Large language models can write, translate, summarize, code, tutor, and converse in remarkably natural language. Their rapid arrival has made AI feel sudden. But this is not one invention, one company's story, or one declared conflict. It is the result of decades of research meeting vast computing infrastructure, global supply chains, business incentives, and national security concerns. That convergence is now reshaping who holds power and who bears the risks. The modern story starts much earlier than generative AI. In 1950, Alan Turing reframed machine intelligence through what became known as the imitation game. In 1955, a proposal by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon used the term artificial intelligence for a 1956 summer project at Dartmouth in New Hampshire. These were milestones, not a claim that AI has a single birthplace. AI developed through changing waves, symbolic reasoning, expert systems, statistical machine learning in neural networks. None simply vanished when the next arrived. Modern AI combines their legacies, while large language models grew especially from statistical approaches to language and neural networks that learn patterns from data. Their origins are distributed across researchers, universities, companies, manufacturers, annotators, and open-source communities around the world. An LLM is a neural system trained on sequences of tokens, small units of text, code, or other data. In simple terms, it learns to predict a missing token or the next likely token. Repeating that prediction at immense scale produces fluent answers. But fluency is not verification. By default, an LLM does not establish what is true, and polished language is not proof of understanding, intent, consciousness, or reliability. A key precursor arrived in 2003, when Yoshua Bengio and colleagues demonstrated a neural probabilistic language model. It learned distributed word representations, helping address limits in earlier statistical language models. The principle was powerful. Words could be represented through learned relationships rather than only fixed symbols or handwritten rules. Later systems applied that family of ideas with incomparably more data, computing power, and model capacity. The decisive architectural shift came in 2017 with the transformer. Earlier sequence systems often processed information in a more step-by-step way. Transformers use attention, a mechanism that can weigh relationships across parts of an input. This made training far more parallelizable, fitting the strengths of GPU and accelerator data centers. It did not make AI infallible, but it made large-scale pre-training technically and economically more feasible. Researchers then found regular empirical relationships between model size, training data, computing power, and language model performance. In 2020, GPT-3 demonstrated broad few-shot abilities with 175 billion parameters, while its creators also documented limitations of web-scale training. Bigger systems could do more from examples in a prompt. Yet scale alone did not make them consistently useful, truthful, safe, or aligned with what people actually wanted. Post-training became just as important. Developers can fine-tune a pre-trained model for particular tasks, then use demonstrations, ranked human feedback, and reinforcement learning from human feedback to make responses better match instructions and preferences. InstructGPT research showed a much smaller, post-trained model could be preferred by evaluators over the far larger base GPT-3 on that study's prompts. Alignment improves usability. It does not eliminate bias, mistakes, or manipulation. The public shock after 2022 was partly a threshold effect. The underlying science was not entirely new, but capable models became conversational, cheap enough to deploy widely, available through consumer interfaces and application programming interfaces, and adaptable to many knowledge work tasks. Translation, tutoring, coding, research assistance, and accessibility tools suddenly reach more people. That broad access is a real benefit, and a reason the consequences extend far beyond laboratories. AI is not only software. It depends on chips, cloud facilities, networking, electricity, cooling, construction, and semiconductor supply chains. The International Energy Agency estimates data centers used about 415 terawatt hours of electricity in 2024, around 1.5% of world consumption. Its base case projects about 945 terawatt hours by 2030. These are scenarios, not a precise forecast for AI alone. because data centers support many digital services, this infrastructure is unevenly distributed. The United States, China, and Europe are the largest data center electricity demand regions in the IEA outlook, while Southeast Asia is growing quickly. Leading AI chips are another choke point. Stanford reports that TSMC fabricates almost every leading AI chip. So access to advanced computing is now treated not just as a commercial issue, but as industrial policy and national security. Modern frontier AI is increasingly industrial and capital intensive. Stanford's 2026 AI Index reports that industry produced more than 90% of notable AI models in 2025. It records 59 notable models from the United States and 35 from China that year. But concentration is not destiny. Open weight models, global researchers, and broader communities can widen access, even as the largest systems require immense capital, cloud capacity, talent, and energy. AI war is a useful phrase only if used carefully. It does not describe one declared armed conflict. It groups together commercial rivalry, competition for chips and cloud capacity, disputes over markets and standards, information influence, cyber operations, and military adoption. The phrase becomes misleading when it reduces everything to a binary US-China contest, or suggests that all AI research is military. The actors are far more numerous. In military settings, AI can assist intelligence analysis, logistics, sensing, target recognition, simulation, cyber defense and offense, information operations, and decision support. AI and autonomy are not the same thing. A system may be autonomous through fixed rules, while an AI system may assist a human-operated platform without independently applying force. The danger grows where speed, opacity, unreliable outputs, or weak human control shape life and death decisions. International governance is expanding, but it is fragmented. UNESCO adopted an AI ethics recommendation in 2021. The European Union's AI Act entered into force in August 2024, with most provisions scheduled to become fully applicable after this dossier's reference date on August 2, 2026. In the military sphere, the UN adopted its first General Assembly resolution specifically on AI in this domain in December 2024. Yet no universal treaty governs lethal autonomous weapon systems. The effects are already social. The International Labor Organization estimates 1 in 4 workers globally is in an occupation with some exposure to generative AI. Clerical work has the highest exposure, while professional and technical roles are increasingly exposed too. Exposure does not mean job loss. The ILO emphasizes transformation is more likely than wholesale replacement. Outcomes will depend on workplace design, training, bargaining power, social protection, and how productivity gains are shared. Benefits and harms will not be evenly shared. Students and researchers may gain tutoring and assistance, but face source verification and de-skilling challenges. People whose work, data, or languages are underrepresented can face consent, privacy, attribution, compensation, and quality problems. Communities near data centers may gain investment and jobs while also carrying grid, water, land use, price, and emissions pressures. Local impacts can be much larger than global averages suggest. Strong benchmark scores do not prove general intelligence, consciousness, stable goals, or dependable reasoning in unfamiliar situations. LLMs can confabulate and fail unexpectedly. Transparency is also declining for some of the most resource-intensive frontier systems, with key details about data, compute, energy, safety tests, and incidents often withheld. Economic, environmental, security, and governance outcomes remain contingent, not pre-written by the technology itself. Large language models emerge from a long convergence of neural language modeling, transformer architecture, massive data, specialized chips, cloud computing, and post-training with human feedback. Their spread can expand knowledge, productivity, science, accessibility, and public services. But the same systems are concentrating strategic infrastructure while creating risks of error, inequality, surveillance, manipulation, environmental strain, and military escalation. The decisive question is not whether AI will matter. It is whether institutions can make its benefits broadly shared and its highest risk uses meaningfully governed. Which safeguard do you think matters most as AI becomes more powerful? Transparency, worker participation, clean infrastructure, human control in military systems, or something else? Thanks for watching.